Hi everyone, welcome back to this video series. Cisco ASA firewalls, pattern matching and stateful pattern matching recognition. Pattern matching is a methodology in which the intrusion detection device searches for a fixed sequence of bytes within the packets traversing the network. Generally, the pattern is aligned with a packet that is related to a specific service, or in particular associated with a source and destination port. This approach reduces the amount of inspection made on every packet. However, it is limited to services and protocols that are associated with well-defined ports. Protocols that do not use any layer 4 port information are not categorized. Examples of these protocols are encapsulated security payload ESP, authentication header AH, and generic routing encapsulation GRE protocol. This tactic uses the concept of signatures. A signature is a set of conditions that point out some type of intrusion occurrence. For example, if a specific TCP packet has a destination port of 1234 and its payload contains the string FF11FF22, an alert is triggered to detect that string. Alternatively, the signature could include an explicit starting point and end point for inspection within the specific packet. The benefits of the plain pattern matching technique include the following: direct correlation of an exploit. Trigger alerts on the pattern specified can be applied across different services and protocols. One of the main disadvantages is that pattern matching can lead to a considerably high rate of false positives. False positives are alerts that do not represent a genuine malicious activity. In contrast, any alterations to the attack can lead to overlooked events of real attacks, which are normally referred to as false negatives. To address some of these limitations, a more refined method was created. This methodology is called stateful pattern matching recognition. This process dictates that systems performing this type of signature analysis must consider the chronological order of packets in a TCP stream. In particular, they should judge and maintain a stateful inspection of such packets and flows. The advantages of stateful pattern matching recognition include the following. It has the capability to directly correlate a specific exploit within a given pattern. Supports all non-encrypted IP protocols. Systems that perform stateful pattern matching keep track of the arrival order of non-encrypted packets and handle matching patterns across packet boundaries. However, stateful pattern matching recognition shares some of the same restrictions of the simple pattern matching methodology, which was discussed previously, including an uncertain rate of false positives and a possibility of some false negatives. Additionally, stateful pattern matching consumes more resources in the IPS device because it requires more memory and CPU processing. Protocol analysis. Protocol analysis or protocol decode-based signatures is often referred to as the extension to stateful pattern recognition. A network intrusion detection system, NIDS, accomplishes protocol analysis by decoding all protocol or client-server conversations. The NIDS identifies the elements of the protocol and analyzes them while looking for an infringement. Some intrusion detection systems look at explicit protocol fields within the inspected packets. Others require more sophisticated techniques such as examination of the length of a field within the protocol, or the number of arguments. For example, in SMTP, the device may look at specific commands such as hello, mail, or CPT, data, RSET, NOOP, and quit. This technique diminishes the possibility of encountering false positives if the protocol being analyzed is properly defined and enforced. On the other hand, the system can generate numerous false positives if the protocol definition is ambiguous or tolerates flexibility in its implementation. Heuristic-based analysis, a different approach to network intrusion detection, is to perform heuristic-based analysis. Heuristic scanning uses algorithmic logic from statistical analysis of the traffic passing through the network. Its tasks are CPU and resource intensive, so it is an important consideration while planning your deployment. Heuristic-based algorithms may require fine-tuning to adapt to network traffic and minimize the possibility of false positives. For example, a system signature can generate an alarm if a range of ports is scanned on a particular host or network. So now my Avast antivirus is coming up here. Okay, the signature can also be orchestrated to restrict itself from specific types of attacks. For example, TCP, SYN packets, heuristic-based signatures call for more tuning and modification to better respond to their distinctive network environments. Anomaly-based analysis. A different practice keeps track of network traffic that diverges from normal behavioral patterns. This practice is called anomaly-based analysis. The limitation is that what is considered to be a normal must be defined. Systems and applications whose behavior can be easily considered as normal could be classified as heuristic-based systems. However, sometimes it is challenging to classify a specific behavior as normal or abnormal based on different factors. These factors include negotiated protocols and ports, specific application changes, and changes in the architecture of the network. A variation of this type of analysis is profile-based detection. This allows systems to orchestrate their alarms on alterations in the way that other systems or end users iterate on the network. Another kind of anomaly-based detection is protocol-based detection. This scheme is related to, but not to be confused with the protocol decode method. The protocol-based detection technique depends on well-defined protocols as opposed to the protocol decode method, which classifies as an anomaly any unpredicted value or configuration within a field in their respective protocol. For example, a buffer overflow can be detected when specific strings are detected within the payload of the inspected IP packets. Virtual private networks. Organizations deploy VPNs to provide data integrity, authentication, and data encryption to assure confidentiality of the packets sent over an unprotected network or the internet. VPNs are designed to avoid the cost of unnecessary lease lines. Many different protocols are used for VPN implementations, including point-to-point tunneling protocol, PPTP, layer 2 forwarding L2TF protocol, layer 2 tunneling protocol, L2TP, generic routing encapsulation, GRE protocol, multi-protocol label switching MPLS VPN, Internet Protocol Security IPSec, Secure Socket Layer SSL. VPN implementations can be categorized into two distinct groups. Site-to-site VPNs enable organizations to establish VPN tunnels between two or more network infrastructure devices in different sites so that they can communicate over a shared medium such as the internet. Many organizations use IPSec, GRE, and MPLS VPN as site-to-site VPN protocols. Remote access VPNs enable users to work from remote locations such as their homes, hotels, and other premises if they were directly connected to their corporate network. Figure 1.6 illustrates a site-to-site IPsec tunnel between two sites, corporate headquarters and a branch office. So you can see here our corporate headquarters, branch office, and here's our VPN tunnel between two ASA firewalls. Figure 1.7 shows an example of remote access VPN. In this example, a telecommuter uses IPsec VPN while a remote user from a hotel uses SSL VPN to connect to the corporate headquarters. Technical overview of IPsec. IPsec uses Internet Key Exchange (IKE) protocol to negotiate and establish secured site-to-site or remote access VPN tunnels. IKE is a framework provided by the Internet Security Association and Key Management Protocol ISA-KMP and parts of two other key management protocols, namely Oakley and Secure Key Exchange Mechanism SKEME. ISA-KMP has two phases. Phase 1 is used to create a secure bidirectional communication channel between the IPsec peers. This channel is known as the ISA-KMP Security Association SA. Phase 2 is used to negotiate the IPsec SAs. Phase 1. Within Phase 1 negotiation, several attributes are exchanged, including the following: encryption algorithms, hashing algorithms, Diffie-Hellman groups, authentication method, vendor-specific attributes. The following are typical encryption algorithms: data encryption standard DES, which stands for Data Encryption Standard, 64 bits long; triple DES, 3 DES, 168 bits long; Advanced Encryption Standard AES, 128 bits long; AES 192, 192 bits long; AES 256, 256 bits long. Hashing algorithms include these: secure hash algorithm SHA, message digest algorithm 5 MD5. The common authentication methods are pre-shared keys, where peers use a shared secret to authenticate each other, and digital signatures with the use of public key infrastructure PKI. Figure 1.8 illustrates the 6-packet exchange in main mode negotiation. In Figure 1.8.2, Cisco ASAs are configured to terminate a site-to-site VPN tunnel between them. The Cisco ASA, labeled as ASA1, is the initiator and ASA2 is the responder. Now, the following are the steps illustrated in Figure 1.8. Step 1, ASA1. The initiator has two ISA-KMP proposals configured. In the first packet, ASA1 sends its configured proposals to ASA2. Figure 1, IKE negotiation. Step 2. ASA2 evaluates their received proposal because it has a proposal that matches the offer of the initiator. ASA2 sends the accepted proposal back to ASA1 in the second packet. Step 3, Diffie-Hellman exchange and calculation is started. Diffie-Hellman is a key agreement protocol that enables two users or devices to authenticate each other's pre-shared keys without actually sending the keys over the unsecured medium. ASA1 sends the key exchange KE payload and a randomly generated value called a nonce. Step 4, ASA2 receives the information and reverses the equation using the proposed Diffie-Hellman group exchange and generated SKYID. The SKYID is a string derived from secret material that is known only to the active participants in the exchange. Step 5, ASA1 sends its identity information. The fifth packet is encrypted with the keying material derived from SKYID. The asterisk in figure 1.8 is used to illustrate that this packet is encrypted. Step 6, ASA2 validates the identity of ASA1 and ASA2 sends its own identity information to ASA1. This packet is also encrypted. Phase 2. Phase 2 is used to negotiate IPSec essays. This phase is also known as quick mode. The ISA KMP SA protects the IPSec essays because all payloads are encrypted except the ISA KMP header. A single IPSec SA negotiation always creates two security associations, one inbound and one outbound. Each SA is assigned a unique security parameter index SPI value, one by the initiator and the other by the responder. Another interesting point is that if the VPN router needs to connect multiple networks over the tunnel, it needs to negotiate twice as many IPsec SAs. Remember, each IPsec SA is unidirectional, so if 3 local subnets need to go over the VPN tunnel to talk to the remote network, then 6 IPsec SAs are negotiated. IPsec can use quick mode to negotiate these multiple phase 2 SAs using the single pre-established ISA KMP SA. The number of IPsec SAs can be reduced. However, if source and or destination networks are summarized, many different IPsec attributes are negotiated in quick mode as shown in table 1.3. In addition to generating the keying material, quick mode also negotiates identity information. The phase 2 identity information specifies what network protocol and or port number to encrypt. Hence, the identities can vary anywhere from an entire network to a single host address, allowing a specific protocol or port. Figure 1.9 illustrates the phase 2 negotiation between two routers that just completed phase 1. So you can see here our initiator ASA1, phase 2 quick mode, and responder. Here's our ASA2 firewall. The following are the steps illustrated in figure 1.9. Step 1, ASA1 sends the identity information IPsec SA proposal, nonce payload, and optional key exchange KE payload. If perfect forward secrecy PFS is used. PFS is used to provide additional Diffie-Hellman calculations. Step 2, ASA2 evaluates the received proposal against its configured proposal and sends the accepted proposal back to ASA1 along with its identity information, nonce payload, and the optional KE payload. Step 3, ASA1 evaluates the ASA2 proposal and sends a confirmation that the IPSec SAs have been successfully negotiated. This starts the data encryption process. IPSec uses two different protocols to encapsulate data over VPN tunnel: encapsulation security payload ESP, IP protocol 50, authentication header IP protocol 51. IPSec can use two modes with either or ESP. Transport mode protects upper layer protocols such as user datagram protocol, UDP, and TCP. Tunnel mode protects the entire IP packet. Transport mode is used to encrypt and authenticate the data packets between the peers. A typical example of this is the use of GRE over an IPsec tunnel. Tunnel mode is used to encrypt and authenticate the IP packets when they are originated by the host connected behind the virtual private network VPN device. Tunnel mode adds an additional IP header to the packet as illustrated in figure 110, as you can see here. Figure 110 demonstrates the major difference between transport and tunnel mode. It includes an example of an IP packet encapsulated in GRE, which means generic routing encapsulation, and the difference when it is encrypted in transport mode and tunnel mode, as demonstrated in figure 110. Tunnel mode increases the overall size of the packet in comparison to transport mode. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing, and subscribing. Thank you.